In this video, we'll take a look at putting together a number of the things that we've seen over the last few videos and learned over the last few years so that we can graph rational functions. So these are some of the steps, and it's not necessary to do them in this order, but this order is fairly useful. First of all, find all the asymptotes, the horizontal, the vertical, and slant or oblique if you want, and also find all the holes. So essentially what you're working with here are any discontinuities, any restrictions to the domain and the range, as well as some things like slant asymptotes, vertical horizontal asymptotes that help you determine some of the shape of the graph. Step 2, find all the intercepts. And of course you want to find the x and the y-intercepts. And of course with both of these steps you're only finding all intercepts or finding all asymptotes if they exist, if they're possible. Step 3 is to make a table of values. And when you're making your table of values, it's a really good idea to choose some points close to your vertical asymptotes, and also choose a really large and a really small value to see the behavior of x being a large positive or x being a large negative number. And once you've done all three of these steps, you're basically going to just draw a smooth curve through all of the points. If you don't have enough points to draw a smooth curve, go back to step 3 and add additional points to your table of values. When you're creating your asymptotes, it's a good idea to use a dotted line, probably a ruler, and I like to draw my arrows so that only one half of them is showing, and that reminds me that the line is getting closer and closer and closer to an asymptote, and I'll show that in the examples that I'm about to show you as well. So let's get to that. Here's the first example. We're going to try and sketch f of x is equal to x squared over x squared plus 1. So let's start off with holes and asymptotes, and we'll start with vertical asymptotes. So vertical asymptotes happen when the denominator is equal to 0. Let's see if that can happen. No, it can't, so no vertical asymptotes. Let's move on to horizontal asymptotes. That's when we check the degree of the polynomial on the top and the degree of the polynomial on the bottom. We see they're the same, so then we go to the leading coefficients which are both 1. So there's a horizontal asymptote when y is equal to 1 over 1, or y equals 1. So if I sketch, and if you have graph paper it's helpful, but there's going to be positive 1. I know the end behavior should move towards this line, y equals 1. No holes, I can't factor and cancel anything, so there's no holes in this case, so I can move on to step 2 and I can go and find the x-intercept, and the x-intercept is when y is equal to 0, and so that happens when the numerator is equal to 0, which is when x is equal to 0. So I know one point on my graph is 0, 0. That's the x-intercept. And likewise, the y-intercept, that's when x is equal to 0. So y is equal to 0 squared over 0 squared plus 1. So y is equal to 0. And of course, it's in the exact same spot. And now I go on to my next step and I try to make up a table of values. So I already know when x is 0, y is 0, so I'm going to need to choose some points. I don't have any vertical asymptotes to choose points from, but I'm going to choose some points that are fairly easy to calculate, like when x is 1 and when x is negative 1, just to get a couple of additional points. And I want to test end behavior, so 10 and negative 10 will help me do that. So I put those back into the original equation, which again is f of x is equal to x squared over x squared plus 1. So 1 over 2 is a half. So 1 over 2, so at 1 it's a half. And negative 1 squared is 1, and negative 1 squared plus 1 is 2, so this is also 1/2. So at negative 1 and at positive 1, it's 1/2. And then at 10, it becomes 100 over 101, which is really close to 1. So at positive 10, it's getting really close to this asymptote. And at negative 10, it becomes 100 over 101, which is somewhere down here, and is also really close to 1. If I need more points to see what this curve looks like, you can add them in. So you can try 1/2 and 2. What you will end up getting is a graph that looks like this. And you'll notice that I use those half arrows to show the asymptotic behavior at positive infinity for the x's and negative infinity for the x's. If you need more points to get more of that curve, again, go ahead and add more points to your table of values. I would suggest a minimum of 5 points whenever you're graphing things. You probably will have days where you need 10 points. So spend some time creating a table of values with quite a few points. That's one of the biggest pieces of advice in this section. So even though we've got some shortcuts, we still will use a table of values approach to really create a number of the points for us. Let's take a look at one more example. So we're going to sketch f of x is equal to 2x over x cubed minus x squared minus 2x. So one thing that you may notice right away is that the numerator and the denominator can actually factor. So if you take out a common factor in the denominator, then these x's can cancel, and so I'm really dealing with a similar equation that looks like 2 over x squared minus x minus 2. I can't forget that I've canceled out the x, so that canceling out the x is leading to a hole. So that hole is when x is equal to 0, and I need to remind myself of that. So that's like the discontinuity here happens, the denominator happens when x is equal to 0. There's a problem, but that problem isn't an asymptote because it got canceled out. That problem becomes a hole. So that hole is when x is equal to 0. And I can actually figure out exactly where that hole is located by plugging x is equal to 0 into this equation, into the simplified equation. So the hole is actually located at when x is 0, y, so this is your y, and I make both of these 0, so I get 2 over negative 2, which is negative 1, and that actually gives me a coordinate for my hole. And I'm going to need that. I'm also going to need to look and see if there's any vertical or horizontal asymptotes. So let's look to see if there are any vertical ones. Vertical asymptotes occur when the denominator is equal to 0, and I've already made part of the denominator of the original denominator equal to 0. Now I will work with the rest of the denominator, which is this part. When is this equal to 0? Well, x squared minus x minus 2 is 0, can cause some vertical asymptotes. And I'll do this by factoring. X minus 2 and x plus 1 could be 0. So it looks to me like I've got 2 places where there are vertical asymptotes. So I'll remind myself of that. So now I can move on to horizontal asymptotes. And those occur by looking at the degrees. And the degree of the top is 1, the degree of the bottom is 3, and when the bottom is bigger than the top, then there's a horizontal asymptote at y equals 0. And I can now move on to intercepts. The x-intercept happens when the y value is 0, and I really only need to know when the numerator is 0, and so I have an x-intercept at x is 0. That will also turn out to be exactly the same point as my hole, so I can't have an x-intercept where there's a hole, so there's actually no x-intercept at all. And for y-intercepts, I can make the x value 0, and solve, and the x value of 0 will give me 0 over 0 minus 0 minus 2, which is 0, but that's actually where the hole is as well, when x is equal to 0, so there's actually no y-intercept for this as well. It's lucky that we've got the location of that hole, because that'll be a nice point to add to our graph. So let's put together what I have so far. Just move this down and add a bit of a sketch here. So I've got this hole which is at 0 minus 1. There's your hole, which turned out to be, there were no x-intercepts, but there's no y-intercepts either, because that's where that hole appeared. And then I know there's a vertical asymptote at x is 2, so I want to explore what that's going to look like. And at minus 1, so I definitely want to create some points in my table of values close to that. And I know the end behavior should be asymptotes of y equals 0. So this is x equals 2 and x equals negative 1. And so now I go and create a table of values, and my suggestion is explore points really low and really high. 10's probably fine. But you also need to explore some points near these asymptotes. So you might want to explore what negative 2 and negative 1.5 do. We know negative 1 won't exist, but what does negative 0.5 do? What does 1 do? What does 1.5 do? And the other side of the asymptote, maybe what does 2.5 do? And I'll leave some room if we need some extra points. So by calculating these, and I put them back into the original equation, I get some values. So at negative 10, I'm at positive 1 over 54, so just right above the x-axis. At positive 10, I'm at 1 over 44, so again here at positive 10, I'm just above the x-axis. At negative 2, I'm at a half, so here's negative 2. There's, let me make that worth 1, so I'm right here. At negative 1.5, I'm about 1.14, so 1.14 is up here somewhere. At negative 0.5, I'm at negative 1.6, so at negative 0.5, that was negative 1, I'm at negative 1.6, somewhere down here. At 1, I'm at exactly negative 1, which is right here. At 1.5, I'm at negative 1.6, so here, negative 1.6. And at 2.5, I'm at 1.14 again. 2.5, 1.14. And now we play connect the dots. So in this, you can kind of separate this into zones. So in this zone here, we can play connect the dots, and I get a curve that looks something like this. I know it's got an asymptote on each end, and then the next zone is kind of in here, and play connect the dots in here. I know I have an asymptote and a hole and some more points, and then the next zone is in this area here, and I know I've got some asymptotes in here as well. So you just really play connect the dots, connect the holes as well in these zones that are formed by these asymptotes. That won't always be true. It could be true that this went this way, had a hole, and went up this way, and then your zone is kind of in between these two asymptotes. But generally speaking, the asymptotes create some boundaries for you for where your graph can go. If you couldn't get it, you just can add some more points. I'll be honest, I used a calculator to calculate a number of these points, and I just want to see that work from you, rather than see you using the table feature on the calculator, which can essentially do the same thing. Okay, we'll see you in class for some more practice.